Okay. Next, we have Lara Bossinger on cluster structures on spinor helicity and momentum twister varieties.
Invitation to the organizers. It's a great pleasure to be here and to have the opportunity to talk to all of these experts on my work, which is joint work with Jianzhong Li, who's in the audience, and the papers on the archive from August. I forgot to put the identifier. So let me just, okay, 1 second, make this work. Yeah, tell you the plan for today. I'm going to briefly mention the motivation, which is the cluster's bootstrap for scattering amplitudes, which we saw in Anastasia's talk. So we'll be brief on that. And then I'll tell you about the spaces, the varieties I'm interested in, which I call spinor helicity and momentum twister varieties. And then how they connect to partial flag varieties and to how they have cluster algebra structure. And lastly, I will mention purely mathematical results that might have application in physics on how these spaces embed into Grassmannians. So let me start with the motivation, the cluster bootstrap. So as we've seen in Anastasia's talk, if we consider planar n equals 4 super Yang-Mills, the cluster variables of Grassmannians for 6 and for 7 were discovered or were observed to be the letters in the symbol alphabet for the scattering amplitude. And this observation has led to the bootstrap program of Dixon and collaborators that now try to compute the amplitude by just looking at the space of all functions on these kinematic varieties, in this case, the Grassmannians, and looking for exactly those generalized polylogs that have symbol alphabet given by the cluster variables, or generalizations of those. So there's a list of people that have worked on this. I entered this story after all of this has been done. So my questions, like kind of naive questions as a mathematician, is like, how does this generalize? Can we generalize away from this toy model, planar n equals 4 super Yang-Mills? If we can do so, so if we take away some of the very beautiful symmetries we observe in this model, what are the kinematic spaces? So what replaces the Grassmannian in this picture? And are there cluster algebras involved? Is there any chance that cluster algebras and cluster variables play a role for symbols of other amplitudes? Okay, so this is kind of the starting point of the project. And then let me tell you about what these generalized varieties are, or how we can go beyond the planar equals 4 super Yang-Mills. And I'm going to refer here to something we saw already in the first talk on Monday, and that's the spinor helicity formalism. So with the spinor helicity formalism, we can pass from a particle configuration in Minkowski space to CP3, and we associate to each particle its helicity spinor, which is going to be a pair of two complex vectors that multiply to 0. And if we consider n particles, this gives us a pair of two by n matrices of full rank, so elements in the Grassmannian 2n. And the condition that the particles are light-like translates to the fact that if we multiply these matrices lambda by lambda tilde transpose, we get the 0 matrix. So with this data, we can define the space of all such pairs as the spinor helicity variety. The spinor helicity variety lives inside a product of two Grassmannians, 2n. And it's the pairs of all elements in the Grassmannians 2n, lambda, lambda tilde, so that when I take lambda and multiply it by lambda tilde transpose, I get the 0 matrix. As we're now inside a product of Grassmannians, we can parameterize this space by minors. So I'm going to define Pij and Pij tilde just to be the 2 by 2 minors of my two matrices. And the space then satisfies some relations or the relations defining this space are the Schouten identities, which are Plücke coordinates in physics language, Plücke relations in physics language, and the second condition is the translation of momentum conservation. Okay. Any questions so far? Okay. All right. Good. So this is our setup. This is the spinor helicity variety, and it models particle interactions of light-like particles. The second player of this talk is the momentum twister variety. So instead of going from the particles to their spinor, to the helicity spinors, we can go to momentum twister space. And we've seen this first part of the talk in Anastasia's talk, which tells me how to get from a particle configuration of n particles, in this case, this is planar n equals 4 Young-Mills, to the Grassmannian for n modulo scaling. So to a momentum twister, we associate a point in CP3, and then the whole system, the configuration is parameterized by 4 minus of its matrix up to column scaling. If we now want to go beyond this model, we can modify it a bit and break some symmetry. For example, we can break the planar symmetry by introducing 2 more points. So instead of n points in CP3, we consider n plus 2 points. So we have these 2 extra points, Zn plus 1 and Zn plus 2. But if we would just parameterize as before by 4 minus, this would just be the configuration of n plus 2 particles. Instead, what we're going to do is we're going to say that our model depends on the 4 minus, where my indices run from 1 to n, or on the 4 minus, where n plus 1 and n plus 2 appear together. So in physics language, Zn plus 1, Zn plus 2 correspond to an infinity twister, and the whole configuration depends on the line that is spanned by Zn plus 1, Zn plus 2, but not on them separately. So in this case, we get, we call the corresponding subspace of the quotient of the Grassmannian for n plus 2 the momentum twister variety. Okay? So these are the 2 varieties that slightly generalize away from the Grassmannian 4n that we would like to study. Any questions? Okay. Sorry? So the ZIs are columns of a 4 by n matrix. It's up to column rescaling. Right. Well,
I wants to hear about GIT.
Yeah. Yeah, GIT quotient in this case. GIT. Well, let's discuss it afterwards. Okay. Okay, so this is the momentum twister variety. If you want, you can also forget about the scaling and just work with the whole Grassmannian for n plus 2. That would also work for my talk. Okay, so these spaces, I mean, I learned about them from the physicists. My physicist collaborators had patiently explain these formalisms to me. But then for a mathematician, it's not hard to realize that these are known spaces in algebraic geometry. In particular, in this case, they're partial flag varieties. So let me tell you what a partial flag variety is. For partial flag variety, I fix the following data. I take a tuple of integers, d1 to dk and n, increasing order. Dk has to be strictly smaller than n. And then the partial flag variety as a set is the set of all flags of vector subspaces in some c to the n. And for each of the di's, I have a vector space of the corresponding dimension in my flag. Now, I can represent such a flag of vector subspaces as a matrix by fixing a basis of c to the n, and then choosing a basis consecutively for all the vector spaces in my flag. And in the matrix, I express the basis elements as rows. So I get a dk times n matrix, such that the first di rows span the di's vector space, the ith vector space of dimension di in my flag. And once I am in the situation of dealing with matrices, I can again use Plücke coordinates or determinants to parameterize the space. So the Plücke coordinate pi1 to pi dj. So I take a dj tuple of indices between 1 to n, give me evaluate on the matrix to the minor, the determinant with corresponding index sets where my minor is always top bound. Okay. So if you haven't seen this before, here's a small example. I can point right, yeah. Here's a matrix that represents an element in a 2, 3, 4 flag variety. So C4 is my ambient space. And if I take the Plücke P1, 3, 4, I just select the columns 1, 3, and 4 and compute the minor. Okay. So these Plücke coordinates, again, I'm talking here to people that haven't seen this before. For the experts, just take it as me setting up my notation. The Plücke coordinates identify determinantal identities called the Plücke relations, and those are quadratic polynomials that vanish on these determinants. But also, they define for me an embedding into a product of projective spaces where the coordinates here are corresponding to the di tuples I can choose in N. And for me, an important ring here will be the multi-homogeneous coordinate ring of the flag variety inside this product of projective spaces. Okay, good. So let's connect this back to the physics and see how the aforementioned spaces are incarnations of partial flag varieties. So to understand the spinor helicity variety as a partial flag variety, what I will do is I will define the pullback of a map that maps the 2n-2n flag variety into the spinor helicity variety. I identify the two minors just on the nose, and so these were the minors of the matrix lambda in SHN. These are the minors of lambda tilde, and there I have a sign flip, and I change the size of my Plücke. Right, so this notation n minus ij is the complement of ij in 1 to n. And you can sit down then and do the exercise and see that, well, Schouten identities translate on the nose to Plücke relations as we expected, and momentum conservation translates to a Plücke relation as well, and this time it involves minors of both sides, of both sizes. And the dimension of this space, SHN, is known. It was studied in a paper, recent paper also by Stumpfeld, Pfister, Massus. It coincides with the dimension of the flag variety, so this is in fact an isomorphism. Any questions? Great. Okay, so for the momentum twistor variety, the map is even easier. I will identify the momentum twistor variety with a quotient of a partial flag variety where the dimensions are 2 and 4 in N, and I think I used this notation and the brackets before for the determinants and the z's, and they're just on the nose Plücke coordinates on this partial flag variety. Great. So now that we have these more general spaces, I called them kinematic spaces before in my title, but then I realized that kinematic space is already like a term used for these vector spaces in Mandelstam, so I changed the title of my talk. So now that we have these spaces and we know they're partial flag varieties, we can move on to the next step and look at their cluster structure. And for that, I'm going to give you a brief reminder on cluster algebras. If you haven't seen them before, I'm happy to talk to you about more details afterwards. Sorry, yesterday I saw the sign cluster algebras on the table. I didn't pick it up, but I'm one of the people that should have picked up that sign. So just to see where we are in math, cluster algebras are commutative algebras. They are endowed with special generators that we call cluster variables. And they are grouped in clusters, which are sets of maximal sets of algebraically independent elements. And they have special automorphisms. The cluster algebra comes with special automorphisms that are called mutations. They map clusters to clusters. So we've seen an example in Anastasia's talk. I'm going to present exactly the same example. I think it's the example that you will find in every cluster algebra talk. The whole data of a cluster algebra is associated with a quiver-directed graph without loops and 2 cycles. So in this case, the quiver is just A2, the one with 2 vertices and 1 arrow. So I associate 2 variables, x1, x2, to my vertices. Then I have a recursive formula that will generate clusters for me. And in this case, clusters are just pairs of variables xi and xi plus 1 that I can generate by this recursive formula. So in this case, here's the computation of what it would look like, just applying the formula consecutive. And in this special case, this is a periodic system. So the 6th variable I come across is again the first. I have a finite number of variables xi that I pick up along the way. And the cluster algebra is a ring, as an algebra is generated by all these variables I pick up inside a field of rational functions of my original variables. Okay, so more generally, this is the definition of what happens with this mutation rule. So the mutation rule consists of 2 parts. One changes the combinatorial data, that is the quiver, and the second changes the variables. So the first picture up here, you should think about it as being a local picture in your quiver. And when you perform the mutation, first you pick one vertex in your quiver, in this case k, and you consider all the vertices that are connected to k by arrows. And then if you find a configuration of paths that go from one vertex I through k to another vertex j, you have to modify the arrows that you have between I and j. And this is the precise rule how to modify. Again, if you haven't seen this before, just take it as there is a rule, and I'm happy to talk to you about it later. And then the second thing you should remember just for now is that whenever I perform this mutation on the quiver, I also change the tuple of variables I associate to the vertices, and I'm exactly going to change one of them, namely the one associated to my vertex k. And the way I change it, or the way I replace this new variable xk prime, is also encoded in the quiver. So I replace it by a binomial where each term corresponds to all the arrows, variables at vertices that have arrows into this vertex k or out of this vertex k. And whenever I have a pair, a quiver, and a set of variables, this is what I will call a seed, and it's one of these clusters, so the variables are one of these clusters that generate the cluster algebra. Okay, so I hope you just stick with this idea that if I give you a quiver and I associate variables to it, this is enough information for you to generate a cluster algebra together with this mutation. So any questions on this slide? Great. If anything comes up, please just feel free to interrupt me. So with this said, how is it relevant, or how is it relevant in this talk? Well, it was discovered back in 2008 that this multi-homogeneous coordinate ring of partial flag varieties is a cluster algebra. And this is a result by Geis, Leclerc, and Schröer. And I want to give you just the input or the basics that you would need to generate this cluster algebra. So I'm going to tell you how to construct the quiver, and I'm going to tell you what are the variables you associate to the vertices. Okay. So this is the example. Okay, I was a bit worried if you could read it. If not, there's plenty of free seats in the first 2 rows. So you can just come closer. This is an example that is sufficiently large enough to tell you about the general combinatorics of how to get these quivers. So the input I need is really just this tuple of dimensions, 2 and 5 in this case, and the ambient dimension 7. So in this example, I'm thinking about flags of a two-dimensional vector space inside a five-dimensional vector space inside a seven-dimensional ambient space. And I'm going to draw on this vertical line down here, which you can think of as the x-axis of a coordinate system, the numbers 1 to 7. And I will remember 2 and 5, which are the dimensions appearing in my flag. And the green graph you can see drawn on the screen is a presentation of a permutation that I can associate to this 2, 5, 7 tuple. And the way it works is as follows. I remember my marked points. And whenever I go from one marked point, so we can think about, maybe let's take this tuple. 2 is a marked point and 5 is a marked point. And all the lines from 3 to 5 next to one marked point until the last one, they don't cross in the diagram. They all just go straight up and turn to the left ones. So what I get here is a permutation where 1 is sent to 7, 1 is sent to 6, sorry, 2 is sent to 7, 5 is a fixed point, 4, 3 as well, and then 6 is sent to 1, 7 is sent to 2. Okay, so if you know about partial flag varieties, this is the permutation you would need to determine the parabolic group that gives you this flag variety. And from this green diagram, I can now associate these index sets that are marked inside the bounded faces and the faces that are unbounded to the left. And the way I got these index sets is by just looking at the corresponding face and remembering which are the lines that pass either to the north or to the east of it. So for example, this face up here, it's unbounded to the left, so I'm going to consider it. And 2 is the only line that is either to its east or north. And this, for example, is a bounded face, so we'll consider it. And the lines above it or to its right are 4, 5, and 2. Okay? So to get to the first information that I need for the cluster algebra, namely the quiver, I'm going to draw a vertex for all of these faces. These are the bounded faces or the ones unbounded to the left. And I'm going to draw arrows according to this rule that maybe you can guess it from the diagram. So if I have a bounded face, then there's an arrow perpendicular to the line just above it, the line below it, to the left and to the right, and we have diagonal arrows going through crossings. Then it looks a bit weird in this face, for example, but if I would move this vertex up here, it would look exactly the same, and the arrow would go through the crossing. And then additionally, I just add 2 more vertices, which, oops, where am I? Here, which are labeled omega 2 and omega 5. Okay? So this is the recipe to cook up the quiver for my partial flag variety. And these index sets, in fact, tell me already what are the elements of the ring that I need to associate. So in order to get to a seed from this combinatory data, I will have to tell you what are the elements I associate to each vertex. What are my cluster variables? And the cluster variables in this case have to be elements of this homogeneous coordinate ring of the flag variety, and they have to be algebraically independent. And the index sets I have here, in fact, correspond to minors of an n by n unipotent upper triangular matrix. And I can use the Laplace rule for determinants to express them in terms of Plücker coordinates. So remember, Plücker coordinates would be minors that are top bound and have range over columns. So with this Laplace formula, I can pass from a minor corresponding to this index set that is always a minor that is right bound in my matrix. So this is the rows. This is the row set of the minor. And then I just make it right oriented in the matrix, and I translate to Plücker coordinates. Okay. So just to make the notation a bit more brief, instead of writing this formula in all of the places in my quiver, I will only remember the maximal term in this expression, and it's maximal in a partial ordering on tableau. So I can think of these two pluckers as filling up columns of a tableau, 2 columns of a tableau, and I would just remember which is the maximal one in this partial order on tableau. And in fact, as such, this tableau would represent me an element of the algebra. It's an element of Lustig's dual canonical basis, and I have a character formula that would reconstruct the whole expression from the tableau. Okay, good. So then in my example before, if I do this computation, I end up with the following pluckers or cluster variables. Whenever there's just one column in this picture, that means the corresponding cluster variable is just a plucker coordinate. And when there's 2 columns, it's a quadratic expression. Okay. So yeah, this is the data I end up for this partial flag. Any questions? Okay. So then let me move to the next part, where to tell you about the results that Janrong and I showed. So from physics, it's very clear that this momentum twister variety has an embedding into a Grossmannian. I mean, we constructed it as a certain subset of a Grossmannian. And in fact, these embeddings generalize to all partial flag varieties. So whenever we have a partial flag variety with dimension d1, d2, and n, we can embed it into a larger Grossmannian. And the way we do it is, for the Grossmannian, we keep the largest d in our tuple. And the n for the Grossmannian will be the n we had before plus the difference between d2 and d1. So this is just the example of a 2-step flag variety, but you can easily imagine how it generalizes. If this would go up from d1 to dk, then I would keep dk here. And the n for the Grossmannian would be n plus dk minus d1. So in terms of the matrices, it's easy to define this map. If you consider an element of the flag variety as a matrix of size d2 times n, then I would send this matrix to a d2 times n plus d2 minus d1 matrix, where I keep m in the first part, and I fill up this matrix with as many columns I need to get to the right dimension. So in this case, as I only have 2, or well, here you would always have basis vectors, standard basis vectors of c to the d2. And the first one you add is e d1 plus 1, and you go all the way up until d1. So on the right-hand side, you would always see a small identity matrix appearing. So if we go through the example, if my flag variety has dimension 2, dimension 4 in c to the 6, so this would be actually an example of both my momentum twister and a spinor helicity variety, then I map it into the Grossmannian 4, and the 8 is 6 plus the difference of 2 and 4. So I go into the Grossmannian 4, 8, and my map, well, just remembers the matrix I had for my element in the flag variety and adds enough column vectors until I have a matrix with 8 columns. Okay. So to understand the image of this map is also not too complicated. The way we constructed the map, you can already see if I take a minor of the matrix in the image that contains the last 2 columns, then it will give me, actually, it will compute a 2 minor in this example of the first of the submatrix that just consists of the first 2 rows of my original matrix. So that means if I start here with a flag variety, remember, that means for 2, 4, 6, the first 2 rows generate a 2-dimensional vector space, and the matrix is of full rank. So if I consider all these minors on the image that contain the last 2 columns, I know that some of them will be non-zero. They cannot all vanish at the same time because I started with a matrix where these first 2 rows gave me a 2-dimensional vector space. So in this set, which corresponds to all of these minors where I select all the last columns I've added, at least one of them has to be non-zero. And now the same is true if I consider minors, 4 minors of just this original matrix M. Right? This was a full rank matrix. So some of those pluckers at least one of them has to be non-zero. So the image, in fact, is the complement of the following 2 vanishing sets in the Grassmannian, where this is the vanishing set of all the pluckers that contain all the columns I've added, and this is the vanishing set of all the pluckers that contains none of the columns I've added. Okay? And in fact, this now describes me an open subset in the Grassmannian that is isomorphic to the image. So I can choose a section of my embedding, projecting this open set onto the flag variety, and that gives me an embedding of the corresponding plucker algebras. So the embedding is essentially, well, you can read it off from these pluckers that I've identified. So in the flag variety D1, D2, N, I have 2 types of minors. The first one in my example would be 2 minors, and I send them to those minors that now contain all the new columns. And the 4 minors just keep the same shape. Okay? Where now here, remember these indices, if I start with a minor in the flag, these indices only run until N. Okay. Any questions on the map? Oops. Where was I? Here. Okay. So then let me present the result we showed in the paper with Jandrong. We focus here on the 2 specific cases of partial flag varieties that are either the momentum twister or the spinor helicity variety. So I have a 2-step flag variety with dimensions 2 and 4 for the momentum twister space, or 2 and n-2 for the spinor helicity variety. And the statement is that the embedding I explained on the slide before of the flag variety into the Grassmannian, it yields an embedding of the algebras. And this embedding of the algebras is compatible with the cluster structure. And I will go into the details of what I mean by the last statement in the last part of the talk. Just to have the statement in general, what is the map I have on the level of the algebras? So for the flag variety, this ring is generated by pluckers of index size either D1 or D2. A plucker of index set of size D1 gets mapped to a plucker with whose index set is I1 plus this interval that runs up until the end. So this is the n of the Grassmannian, if you like, the ambient dimension of the Grassmannian. And for the second type of pluckers that are of size D2, I just send them to the corresponding plucker in the Grassmannian. Okay, good. So then let me tell you about what I mean by compatibility with the cluster structure. Okay, and this is the statement. This is essentially the same theorem, just stated a bit more precise. So I'm gonna go over it slowly, and please interrupt me at any point if you have questions. So remember, I told you for a cluster algebra, I always need this information of a seed that is a quiver together with a tuple of variables. And S is my notation for the seed. So S0F is the notation for the seed I need to construct the cluster algebra of the flag variety. So QF is a quiver, an oriented graph without 2 cycles and loops, the one I draw on this diagram of a permutation. And XF denotes a tuple of the corresponding cluster variables which had these expressions in either Plückers or quadratics in Plückers. So, oh yeah, and maybe I should have mentioned before, a Grassmannian is an example of a partial flag variety, just in case it's not clear. So if I just have one dimension where I have support in my flag, this is a Grassmannian. So the construction I gave you to construct a seed for a flag variety also works for Grassmannians, just that I have just one tuple of indices. There's just one mark point at site, well, at place K for the Grassmannian Kn. So there is so for the Grassmannian, I can construct the cluster algebra given the same combinatoric machinery. And the statement is that within all the seeds I get for the Grassmannian, I can find one particular one that I denote as GR. Again, it's a pair, a quiver, and a set of variables that satisfies the following conditions. The quiver for the flag variety is a full subquiver in the quiver of the Grassmannian. And by that I mean that I obtain it by freezing certain vertices. And by freezing, I mean that after freezing, I don't allow mutation at this particular vertex anymore. And I eliminate n-3 times n-5 vertices. And the second statement is that if I consider the embedding of the algebras that I called phi, and I consider the images of all these cluster variables that I have for the flag, then they land inside the tuple of cluster variables for the Grassmannian. And the statement that is not on this slide, but that is true, is that they land exactly on the corresponding vertex of the quiver. And my last slides are explaining this statement in an example. So I hope that would clarify things, but I can also see if there's any questions about the statement. Yeah, a specialization. You can think about that as a specialization. Okay. So the statement I've given you here is the statement for this case of the spinor helicity variety. So it's the n-2 flag variety. A similar statement is true for the momentum twister variety. The situation just becomes much simpler. So instead of freezing n-5 vertices, I just need to freeze 1. And I just need to eliminate or specialize in 2 vertices. And the strategy for the proof of this theorem is exhibiting an explicit mutation sequence to this seed SGR. So essentially, all I need to do is I need to tell you what this seed SGR is and show that it has the corresponding properties. And as I mentioned, the Grassmannian is a special case of a flag variety. So I can easily compute a nice initial seed for this Grassmannian, and then we show a mutation sequence from this nice initial seed from the Grassmannian to the seed that I actually need. And in this case, it's achieved by n times n-4 times n-5 over 2 mutations. And for the case of the momentum twister variety, I only need to do 2 mutations to get to the special seed. Okay, so here's the first example. On the left-hand side, this is the data I need for the Grassmannian 4-8. So if I would just run this combinatoric machinery, it would give me this quiver together with a set of Plücker coordinates. So in this case, you can notice that at all vertices, I just have one column tableaus, which just correspond to Plücker coordinates. And the index sets I've written down are exactly the index sets of the Plücker variables. And then there's some colors in this graph. I don't know if you can see them, but we can already observe that at many vertices, the index sets that appear only contain indices from 1 to 6. And those were exactly the Plücker coordinates that are images of Plückers of the flag variety, right? So my flag variety in this case is 2, 4, 6. So I have 2-dimensional minors, 4-dimensional minors, and I can choose indices from 1 to 6. And all the green vertices, or teal, are already of this form. So down here, I can see images of 4 minors of the flag. And up here, you can observe that these 3 already contain the indices 7 and 8 together. So these 3 are images of 2 minors in the flag variety. Okay? Because I have a 2 minor, I would just add 7 and 8 to make it a 4 minor, and these are images. And then I have, in this case, 5 more vertices that do contain 7 or 8 separately, so they are not images of any minors of the flag variety. And in fact, these are the ones where I will perform mutations, or more precisely, I will only pick a subset, namely these 2, to mutate. So in this picture, what I will do to get the quiver for the flag variety is I will do mutations at the vertices 7 and 11. And this is the outcome of this mutation rule. So if you take the mutation rule I gave you at the beginning of the talk and you apply it consecutively in 7 and 11, you end up with this quiver. And I've also computed the change in cluster variables and compactly stored the information in these tableaux. But what you can observe after these mutations is that now the tableau I have on these pink vertices, 7 and 11, are also images of Plückers or expressions that I had for the flag variety. So they satisfy the condition that each column either only contains indices from 1 to 6 or 7 and 8 together. And in fact, what we checked is then, or what you can check in this example, that all the colored vertices on the right side are exactly images of the Plückers or the cluster variables we had for the flag variety in the initial seed. Okay, so if I now freeze this vertex 11 and I specialize these 3 vertices that are in black, or for simplicity, you can eliminate them, what you will see here is exactly the initial quiver with the right cluster variables for the flag variety. Okay. And this example is in fact the only case where the momentum twister variety and the spinor helicity variety are both the same flag variety. 2, 4, 6 appears in both sequences, 2, 4n and 2n minus 2n. So the case of the momentum twister variety generalizes directly from this picture. The Grassmannian quiver for the momentum twister variety will only extend here to the bottom if you grow in n, and you will always do mutation at these 2 vertices. And then you delete exactly and freeze in exactly the same way. So for the other sequence of the 2 n minus 2 flag varieties, the situation is a bit different because the Grassmannians are always these middle Grassmannians. So for the spinor helicity variety, we will always have Grassmannian 4 and some n, and it only grows in one direction. For the spinor helicity variety, we always embed into middle Grassmannians, so the quiver goes in 2 directions. And what we observed here is the following pattern for this mutation sequence. So the initial seed for a Grassmannian will always look like this. It's a grid of k times n minus k vertices with these arrows and one extra frozen vertex at the bottom. And in general, what is true, again, the green vertices, I don't know if you can see, it's the first 3 vertices in the top row and all the vertices in the last 2 rows. They satisfy the condition that they're images of plukers of the flag. So in the top row, we will observe that in this case, we're in the flag 8. So going to the Grassmannian, we add 9, no, wait, we are 6, 8. Yeah, we add 9, 10, 11, and 12. So we can see the 2 minors or images of 2 minors whenever in a pluker 9 and up to 12 appear all together. And this is true for these 3 cases. And in the bottom 2 rows, 9 up to 12 don't appear at all. So these are images of the 4 minors in the flag. And then we identify what we call a mutation grid inside this quiver. And it is this rectangle that I marked in pink. And this is the sub part of the quiver. We will perform mutations to get to the quiver for the flag. And the mutations that we perform, they always start in this bottom right corner and go up column-wise, like this. And after we've done the first round of these mutations, we identify in these 2 places, in the top row, variables that are in fact images of flag minors. So then we proceed, repeating the same mutation pattern, just as we stop right before we would actually mutate at the image of a pluker coordinate or a cluster variable of the flag. Okay, so we do mutations 9 to 11, 15, 17, and so on up until 29. After this round of mutations, 29 and 23 have the desired form. So in the next round of mutations, we would stop at 22. Okay, so if we do this mutation, we run through all of it. The top row here and the vertices 16 and 10 will be vertices that have images of cluster variables of the flag variety. And after the whole mutation sequence, the quiver looks like this. I've rearranged the vertices a bit. So the pink vertices are actually all over the place now. For example, 28 was here and now appears on the left side. 29, oops, sorry. 29 to 10, 29, 16, 10 appeared, oh, wrong direction, appeared on the right side. 29, 16, 10, and they are vertices that I will freeze. And then the green vertices are the ones that were already green on the other side. Okay, and in this case, you can see that my quiver, in fact, separates into 2 parts. After I perform the freezing necessary to see the subquiver for the flag, there's a whole part of the quiver that is no longer connected to the mutable part on the right-hand side. So I can, if I just specialize all these variables to 1 or delete them from the quiver, I can see the cluster algebra of the flag variety sitting inside the cluster algebra of the Grassmannian. Okay. Any questions on this procedure? Yes, yes, it's exactly the same in this case. Okay, so then on my last slide, I just want to summarize a bit or tell you what are the next steps to take with these results. So on the first item, this project rose out of the program that Anastasia presented on Monday, and the desire to generalize away from the Grassmannian as the space modeling the kinematics. And before this project, I was actually working with James Drummond and Ross Glue on this idea of computing the symbol alphabet or recovering the symbol alphabet for the spinor helicity variety. So we did computations for n equals 5. N equals 5 is published, n equals 6 we didn't really go all the way through because of computational challenges we encountered. But so that's definitely one item on the list, using these results now to trying to push further and see how the cluster structures can help us recover the symbol alphabet that's already known in the literature. And for n equals 5, we were successful in the sense that just from the tropicalization of the space or its cluster structure, we could observe a nice combinatoric subset of variables that match the symbol alphabet. For n equals 6, the problem gets harder because this is the first case where the flag variety has an infinite number of cluster variables. So we have to be a bit more careful, but we already implemented some successful methods of going to limit rays in the tropicalization. So these methods can be applied. The second point is purely mathematically. The embeddings of flag varieties into Grassmannians, they generalize for arbitrary partial flag varieties. So it's a very natural question to ask if the cluster structure is compatible also in this case. We conjecture that it is, but exhibiting the mutation sequences gets more complex. And I have a student working on that right now, so I really hope it will be successful. It's the same map that I presented, essentially. Let me just go here. So just that instead of having D2 here, you would replace it by DK, the last dimension of your vector space. And you always have to fill up the matrix just by the difference of DK and D1. Yeah, so let me just write this here. So if my flag variety is now any partial flag, D1 up to K into N, I embed into a Grassmannian where I keep DK as the dimension for the Grassmannian, and N for the Grassmannian would be N plus DK minus D1. So the way I think about it is this is the number of columns I need to add to make a D1 minor a DK minor. And yeah, the map looks exactly the same way, just adding identity columns. Right, so yeah, that's the second bullet point, and I hope my student will work it out. The third bullet point is based on interesting conversations I had with Matteo. So Matteo and collaborators, I think maybe Lauren Williams will tell us about these results tomorrow, show that the cluster compatibility conjecture is true for the tree amplitahedron, which means that tilings of the tree amplitahedron have the property that the facets of tiles are determined by compatible cluster variables, and compatibility for cluster variables means that they appear in some cluster together. And it's been a conjecture, I don't know, I attribute it to Matteo, but if I should put some other names here, please let me know. There's the conjecture that this cluster compatibility also works for the momentum amplitahedron. And it looks promising that the cluster structures we can see on the spinor helicity variety is exactly the one we would need to use for cluster compatibility. And then the last bullet point is another very interesting direction I'm pursuing right now with Jan Rong, James Drummond, and Omar Gurdogan. And that's the following. So to obtain the momentum twister variety inside the Grassmannian, so momentum twister n inside Grassmannian 4 n plus 2, I told you we can think about this as either from the Grassmannian n adding an infinity twister, but we can also think about it as going down from the Grassmannian 4 n plus 2 by imposing a certain vanishing condition of these differential operators on the zi's. So in this case, what does this mean? This means that I'm free to move my n plus first point along the line spanned by n plus first and n plus second and vice versa. So there's a similar procedure that I can do to force two of the momenta to be collinear, and it translates into this condition. So if I have my configuration of n particles and I think about the momenta, I want to make the nth and the n minus first collinear, and I can do that by allowing to move the nth along the line spanned by n and z1, and the n minus first along the line spanned by n minus 1 and n minus 2. And this would represent a particle configuration where now there's a particle that is massive, no longer light-like. So interesting math questions coming up are if we can describe the kinematic spaces in these cases, if they're known subvarieties of partial flag varieties or Grassmannians, and if they have a cluster structure as well. That's all I wanted to say. Thank you very much for your attention.
I don't understand this notation with the derivatives here. So the zi's are vectors of length 4, no?
The zi's are points in CP3. Yeah.
What do you mean by ddzi?
So I think about, so I have my points. And my whole configuration depends not only on the points, but also the lines they span. And if this is my zi plus 1, the vanishing of zi del zi plus 1 means that I can now move zi along this line. And if it vanishes, that will not change the configuration.
Just don't understand the notation.
Yeah, well, the notation, I adopted it from the physicists. But this is what it should mean, being allowed to move one point along the line.
So you have Grassmann, for example, Grassmann, you have write it as a group and evaluate it on web matrix, then you get a polynomial in sin xij, and then this is you take like sometimes like something like an inner product.
Okay, maybe we should talk about it later.
Yeah. That's okay. Let's thank the speaker.